Hello Algebra 2 students. This video is the last unit in Algebra 2 and Trig, Unit 11, Statistics. Each section will cover a different standard that the Regent could test you on within Algebra 2, within Statistics. So, a game spinner is divided into 6 equal regions. Miles. To win, the spinner must land on number 6. After spinning the spinner 10 times and losing all 10 times, Miles complains that the spinner is unfair. So Miles' empirical probability was 0 out of 10. At home, his dad ran 100 simulations of spinning the spinner 10 times. The probability of winning each spin is 1 out of 6. The output, so the theoretical probability, is 1/6. The output of the simulation is shown in the diagram below. Which explanation is appropriate for Miles and his dad to make? So first, let's determine whether it's fair or unfair. To do that, it should fall within the middle 95%, and to find the middle 95% interval, you would take the mean and subtract 2 standard deviations, take the mean and add 2 standard deviations. The mean and the standard deviation can be found right there. Okay, let me put that in my calculator. You get negative 0.061 and 0.375. So that would fall somewhere here and somewhere here, and this is your middle 95%. Does 0 fall within that middle 95%? Yes. So the spinner was likely not unfair. So we're going to cross out the ones that say unfair. And now we have to choose between the two that are not unfair. The spinner was likely not unfair since the number 6 failed to occur in about 20% of the simulations. Yeah, that's true. Spinner was likely not unfair since the output the player wins once or twice in the majority of the simulations. No, that's not true. Okay. Robin flips a coin 100 times. It lands heads up 43 times. And she wonders if the coin was unfair. She runs a computer simulation of 750 samples of 100 fair coin flips. The output of the proportion of the heads is shown below. Does the results of the simulation provide strong evidence that Robin's coin is unfair? We're going to do the same thing. To find the middle 95% interval, you're going to take the mean, subtract 2 standard deviations, take the mean, add 2 standard deviations. Let me put that in my calculator. Okay. You would get 0.401, 0.597. Does 0.43 fall within that middle 95%? Yes. So, you could say, since Robin's empirical probability was 0.43, and it falls within the middle 95% interval, and I'll write the middle 95% interval, it is likely that Robin's coin was not unfair. Okay? A researcher randomly divides 50 bean plants into two groups. He puts one group by a window to receive natural light, the second under artificial light. He records the growth of plants weekly. Which data collection method is described in this situation? Since you have two groups, one is a control group, one is an experimental group, that is a controlled experiment. Usually if you have a scientist or a scientific researcher, then that would be a controlled experiment. But yeah, if you have two groups, one is a control group, one is an experimental group, and you're looking for a cause and effect, that's controlled experiment. Which investigation technique is most often used to determine if a single variable has an impact on a given population? Single variable sounds very controlled to me. Has an impact, a cause. That's controlled experiment. Controlled experiment has cause and effect. Chuck's trucking company has decided to initiate an Employee of the Month program. To determine the recipient, they put the following sign on the back of each truck. How's my driving? Call 155 driving. The driver who receives the highest number of positive comments will win the recognition. Explain one statistical bias in this data collection method. Just remember, self-selection leads to statistical bias. Think about it. If you are driving and you have a number and a driver is not affecting you at all, they're driving fine on, but they're in front of you, you see this number, are you going to call? No. You're not going to waste time out of your day to call that. But let's say you have your kids in the car and this driver is swerving everywhere and you're scared for your life. I mean, first you should probably call the cops, but no, you would probably call the number as well, report them to the company. So, who's going to call on this driver? Is it going to be people that are happy with the driving or people that are not? It's going to be people that are not. So you could say, self-selection leads to statistical bias. The people with complaints are more likely to be calling. Okay, candidate for political office commission poll. His staff received responses from 900 likely voters. 55% of them said that they would vote for the candidate. The staff then conducted a simulation of 1,000 more polls of 900 voters. Assuming that 55% of voters would vote for the candidate, the output of the simulation is shown in the diagram below. Given this output, and assuming 95% confidence level, the margin of error for this poll is closest to. So your formula for margin of error, you have to memorize this, is z times the square root of p times 1 minus p over n. Z is your z-score, p is your percentage, and n is the sample size, the population percentage. So z is always, on the region, they never not ask 95%. So you know the z-score of 95% is exactly 1.96. So if you want to memorize it as this formula, you can. You don't have to remember z. The only reason I teach it that way is because let's say you do go into AP Stats, you do have to expect, different confidence levels. So 1.96 times the percentage was 55% over the sample size. See responses from 900 likely voters. Don't get confused by the simulation. The simulation, they could add more. So 900 was the sample size. Put this in your calculator. If you're putting this in your calculator, make sure you have parentheses around your numerator. In that case, actually, it wouldn't affect it, but because you're just multiplying and then dividing one term. Okay, and you end up getting 0.032502999229. So it's about 0.03, the margin of error. Okay. In this one, they want you to find the plausible interval contained in the middle 95%. Again, middle 95%. You're going to take the mean, subtract 2 standard deviations. Take the mean, add 2 standard deviation. Mean is right here, standard deviation is right there. They could say mean, they could say average, right? Synonyms. Okay. So you got 0.134 to 0.374. That would be this interval right here. Okay. Public opinion was conducted on behalf of Mayor Ortega's re-election. Shortly before the election, 264 out of 550 likely voters said they would vote for Mayor Ortega. The rest said that they would vote for his opponent. Which statement least predicts least appropriate to make according to the results of the poll? So let's do this. 264 out of 550. You got 0.48. There's a 48% chance that Mayor Ortega will win the election. So, according to the Regent answer key, the answer was number 1. Have there been mistakes made on the answer key? Yes. Personally, since this is using, sample data to calculate what's most likely, that would be point estimate. So the point estimate would be 48%, but again, with a question like that, at least you have a 50-50 chance of getting it right. Okay. Elizabeth waited for 6 minutes at the drive-thru. at her favorite fast food restaurant the last time she visited. She was upset about having to wait that long and notified the manager. The manager assured her that her experience was very unusual and that it would not happen again. Study of customers commissioned by this restaurant found an approximate normal distribution of results. The mean wait time was 226 seconds, and the standard deviation was 38 seconds. Given the data and using a 95% level of confidence, was Elizabeth's wait time unusual? Justify your answer. Unusual, unfair, right? All middle 95% interval. So you take the mean, add and subtract 2 standard deviations away. The mean is 226. The standard deviation is 38 seconds. So 226 minus 2 times 38. 226 plus 2 times 38. You get 150, 302. Okay? Elizabeth's wait time was 6 minutes. So how many seconds is 6 minutes? There's 60 seconds in a minute. So 6 times 60, 360. Was Elizabeth's wait time unusual? Yes. Elizabeth's wait time was unusual since 360 seconds falls outside of the plausible or middle 95% interval, and now we just restate the middle 95% interval, 150 to 302. Okay. The price of postage stamps this year, in the year since the end of the World War II, is shown in scatterplot below. What equation best represents this model? So, what equation looks like this? That looks like an exponential to me. So, it definitely doesn't look like a sine wave, right? So, what you're going to do, we could do it's definitely not linear. If it was linear, then or really the line of best fit, if it was linear, would have been this, right, kind of through that little point, but you'd be missing these points. So what you could do, kind of estimate where these points are, and then do an exponential regression. It's not going to be perfect because it's an estimate, but we have, let's say, I'm looking at this point here, 1, 2, 15, 3, 40, 4, or we could say 5 because it's kind of in the middle there. And again, you're estimating, so it's not going to be perfect. 43, 7. $58, 10. And you don't have to put every point, just put a bunch. 60, 15. 20, 65, 22. 81, 35, or 33, 34, I'll say. 90, 39. 95, 50. Okay, that's enough points. So we're going to go to stat, edit, input all of our x's into L1. The more points you have, the more accurate it's going to be. Try your best not to make mistakes, right? Okay, now you're going to go to stat, calc, xbreg, and you get y equals 1.65 times 1.03. The one that's closest to would be 3. Okay? Okay. We have to write an exponential regression formula, so we're going to do exactly what we just did. This time it's easier because we don't have to estimate points. To clear your list, you could go up to L1 and clear, up to L2, clear, and then press enter. But 0, 0.5, 1, 2, 3, 4, 6, 4, 10, 15, 60, 260, 1,130, and 16,380. Go to stat, go to calc, go to xbreg. L1 is xlist, ylist is L2. Calculate, and it says to round all the values to the nearest thousandth. So y equals 3.375 times 4.787 to the x. The researchers know that people are likely to suffer from foodborne illnesses if the number of spores, which is y, exceeds 100. Use the exponential regression equation to determine the maximum amount of time to the nearest quarter hour that the meat can be kept at room temperature safely. So it exceeds 100, so we can start at 3 at 100. I used x and y because that's what was used here. Isolate the base. Convert to log base form. So log base argument equals exponent. Put that in your calculator. I go to math. Go to log base. Type in 4.787. 100 divided by 3.375. And you get that x equals 2.164101411. It says to the nearest quarter of an hour. X is in hours. So the nearest quarter would probably be 2.25. Personally, I wouldn't be risking having food after 2.25 hours because they had us round up. But maybe that's just me. Normal distributions. What proportion? Okay, with normal distributions, often you're going to do normal CDF, right? And remember, normal CDF, lower, upper, mean. You use that mu symbol to represent mean, and then lowercase sigma for standard deviation. What proportion of ball bearings will have a diameter less than 3.7? So if it's less than 3.37, Is 3.37 going to be your lower or upper? It's going to be your upper. Your mean is 4. Your standard deviation is 0.2. And now your lower. Think about this. We don't know what these balls are being weighed as, right? But this is normally distributed, right? And what would happen if we selected 2, like a weight of 2, and it just so happened that there was a ball that weighed 1.9? You wouldn't be counting that in the percentage, right? So, you know a ball can't weigh a negative, right? But what would happen if you added that percentage, all the balls that weighed negative, right? This is just finding you the percentage. So if you're adding the percentage of all the balls that are negative weight, which it's impossible to have a negative weight, that's 0%. So the reason we're going to use a negative is so we know adding 0% won't affect it. But at least we know every other weight that does exist is being incorporated in that percentage. So I'm going to say negative 1,000. The same thing goes the other way. We're going to use a very high number. So I go to second vars on your calculator. It's VARS. Second vars, normal CDF. Negative 1,000 is my lower. Upper is 3.7. Mu 4. Standard deviation 0.2. And you get 0.066807287. That's approximately option 1. Okay. 2 versions of a standardized test are given, an April version and a May version. The statistics for the April version show a mean score of 480 and a standard deviation of 24. Okay. The statistics for the May version shows a mean score of 510 and a standard deviation of 20. Assume the scores are normally distributed. Joanne took the April version and scored in the interval 510 to 540. What is the probability to the nearest 10,000 that a test paper selected at random from the April version scored in the same interval? Maria took the May version. In what interval must Maria score to claim she scored as well as Joanne? So we want to find the probability of 510 to 540 on the April version. So you're going to do normal CDF of your lower 510, upper 540. Your mean score is 510. Standard deviation is 20, right? This is for the April version. Did I use April? Nope. The April version showed 480 and 24. So we put that in our calculators. You go to second vars, normal CDF, 510, 540, 480, 24. Let's paste that. So 0.0994401,591. So about 9%. So near 10,000, 0.0, so 100th, 10th, 100th, 1,000th, 10,000. Maria took the May version. In what interval must Maria score to claim she scored as well as Joanne? So, we're going to have to find, I believe, the z-score. So you take the scores, you subtract the mean, divide the standard deviation. So 510 minus, for the May version, for the April version, that was 480 over 24. You're also going to do the same thing for 540. So 510 minus 480 divided by 24, 1.25. 540 minus 480 divided by 2 is 2.5. So between 1.25 and 2.5. So we have the two z-scores. We're going to have to find that for the May version now. So we want to find between 1.25 to 2.5. So on the May version, we're going to use the same formula. So now we have 1.25 equals x minus, your mean on the May version was 510 over the standard deviation, which is 20. Can multiply by 20 on both sides. Add 510 to both sides. And you get that x equals 20 times 1.25 plus 510 is 535. We're going to do the same thing for 2.5 standard deviations. So 2.5 equals x minus 510 over 20, multiplied by 20. Okay, yeah, just making sure we're using the right one. Add 510. So 20 times 2.5 plus 510, you get 560. So on the May version, Maria must score a 535 to 560. That is equivalent to getting a 510 to a 540 on the April version. Okay, so these are your two answers. It wasn't so difficult, you just have to, remember to use the z-score formula, because if it's normally distributed, they might be normally distributed in different areas, right? Okay, hopefully this helped. Have a great day, everyone.